Good morning, students. Today we are going to discuss about mutual induction, right? Okay, students. Before that, just I am recalling the self-induction. Okay, students. Okay. So see the self-induction. An electric current flowing through a coil will set up a magnetic field around it. Therefore, the magnetic flux of the magnetic field is linked with that coil itself, right? So if this flux is changed by changing the current, an EMF is induced in the same coil, right? See that flux is changed by changing the current, an EMF is induced in the coil. This phenomenon is known as self-induction, and the EMF is induced is called as self-induced EMF. Okay, students, so we discussed in last class now. Yes, right. And that induced EMF or self-induced EMF formula, E is equal to minus L into di by dt, rate of change of current, right? So that is di by dt. So if I am taking that L going to this side is equal to minus E divided by di by dt. Yes, this is the self-induction is formula. Okay, so based on this, there is example problem. Yes, and finally see this L which is equal to mu naught n square A into L. Yes, so this is the self-induction formula. L is equal to mu naught n square AL, right? So based on this example problem, okay, so we know the L and S, this induced EMF, self-induced EMF formula. Okay, so based on this formula only, example problem 1.0. See this, a solenoid of 500 tons is wound on an iron core of relative permeability 800. So 1500 tons is wound on an iron core of relative permeability 800. The length and the radius of the solenoid are 40 centimeter and 3 centimeter respectively. Calculate the average EMF induced in the solenoid if the current in it changes from 0 to 3 ampere in 0.4 second. Okay, so we have to calculate the average EMF, that means average induced EMF in the solenoid. Okay, okay students, right? See this from the question, datas N is equal to 500 tons, relative permeability 800, length is 40 centimeter, therefore converted into meter 0.4 meter, and that yes, radius equal to 3 centimeter, converted into meter 0.03 meter, and that yes, change in current 0 to 3, therefore 3 to 0, the total current is 3 ampere, and the time is 0.4 second. 0.4 seconds. So this is the data, right? This is the data. Okay students, so with the help of this data we have to calculate the induced EMF. Yes, according to the self-induction formula, L which is equal to mu n square A into L. So this is the self-inductance formula, mu n square A into L. Yes, if mu is equal to is nothing but product of mu naught into mu r, permeability in free space and relative permeability. Therefore, yes, if I am taking instead of mu, I am substituting mu naught mu r, right? And n, next n square, no, instead of n, yes, is equal to n by L, because capital N is equal to n into L. sorry, n divided by L. So therefore I am taking that n is equal to n by L. Therefore n square by L square. N is equal to n by n, but here n square, therefore I am taking square n square divided by L square into A into L. L square cancel, therefore I can get mu naught mu r n square. A is equal to area of cross section, therefore area of the coil pi r square s divided by L. So this is the self induction formula from this one. Okay students, right? Okay, now yes, just I am going substitute the values. Okay, see this again. L which is equal to, yes, L which is equal to mu naught mu r n square pi r square divided by L. Mu naught value 4 and mu r is 3.14 into 10 power minus 7, right? And n, sorry, mu naught is equal to 4 pi, yes, 4 into 10 power minus 4 pi into 10 power minus 7 value, mu naught value, that's why 4 into 3.14 into 10 power minus 7, and the mu r is given, right? Therefore 800, relative permittivity is given 800, and n 500 is given, therefore n square 500 square, and pi value 3.14, and r square 3 into 10 power minus to the whole square, right? So therefore 4 into 3.14 into 800, yes, I can get 283,956.48 into 500 square into 10 power minus 7, and yes, into 3 squares also I can get this value. So therefore 0.4, here 10 power minus to the whole square, 10 power minus 4, therefore 0.4. Okay students, so except 500, all the values multiple, you will get this one and divide by 0.4, right? Okay students, therefore yes, see this again, you will simplify, you will get 1.77, right? Henry, because Henry is the what? Henry is the unit of self induction. Okay students, so with the help of L, we have to find out EMF, induced EMF. Therefore induced EMF formula is equal to L di by dt, right? Right, okay, therefore L is equal to is given, no, here 1.77, di value is given into 3, and divide by dt value also is given, that is 0.4, therefore divide by 4, therefore 1.773 into 1777 into 3, 5.31 divided by 0.4, yes, you will get 13.275 volt. This is the induced EMF. This is what? Induced EMF. Okay students, first we have to, so first we are calculating, yes, which value? L value, and with the help of L value, yes, we are finding out induced EMF. Okay students, right? Any doubt? No. Okay, and the next question is, the self inductance of an air core solenoid is 4.8 millihenry. So here air core of solenoid is 4.8 millihenry. Okay, if its core is replaced by iron core, then its self inductance becomes 1.8 henry. Okay, and find out the relative permeability of iron. Find out relative permeability of iron. Okay students, therefore here 2 is self inductance given. So based on this question, yes, it is easy question, therefore see that L is the self inductance, no, So for air core, I am taking L air is equal to 4.8 into 10 power minus 3 Henry is given. For iron core, the inductance is 1.8 Henry. Yes, therefore, see the question, find out the relative permeability, right? Therefore, it is easy, no? For inductance, air core, mu naught n square Al formula, that is equal to 4.8 10 power minus 3 Henry. For iron, yes, therefore medium present, therefore mu n square Al. Mu is the relative permeability in medium. Iron is medium, no, that's why mu n square A into L. Yes, instead of mu naught mu r, because mu is equal to mu naught into mu r n square Al. Yes, that is equal to 1.8 Henry is given. Therefore, the help of this one, yes, if I am taking that both formula same, no, so therefore what is the ratio? Is mu r I am taking, therefore this equation from this equation, if I am taking this mu r which is equal to, right, ratio of self inductance in medium to the air, that's why L iron divided by L air. Understand? Because relative permeability. Okay, students. Therefore, what is inductance for iron? 1.8 divided by 4.8 into 10 power minus 3. You will get 375. Yes, and 0 will get 10 power minus 3 will come. And if you simplify, you will get 375. There is no unit for relative permeability. Okay, students, right? Okay, students, see this relative permeability. I'll show you. For relative permeability, see this one, mu is equal to mu r and mu naught into mu r. Yes, from this one we are taking that what will come, mu r will taking, yes, this mu naught going to downwards, right? Yes, with the help of this relation, only, yes, mu r which is equal to, mu r is equal to this one divided by this one. Okay, students, right? Okay, the next topic is mutual induction, right, or mutual inductance. Okay, students, right, see a small introduction about mutual induction. Okay, when the strength of a current in one of the two adjacent coil changes, when the strength of the current in one of the two adjacent coil changes, a change takes place in the magnetic field around. The strength of the current in one of the two adjacent coil changes, a change takes place in the magnetic field around it. Okay, so as the result of this, EMF is induced in the second coil. So this phenomenon is mutual induction. That means if we are taking the two coil, the one coil is connected to, yes, battery. If you change the current in one coil, yes, the magnetic flux also linked with the second coil. If you change the current in one coil, the magnetic flux changes in the secondary coil, and the second coil or secondary coil produces induced EMF. Yes, this is called as mutual induction. This is called as mutual induction. Okay, students, do you understand? That is mutual. If you any changes in one coil, there is also changes in neighboring coil. Okay, right. See this. Mutual induction is the phenomenon of production of induced EMF in one coil due to the changes of current in the neighboring coil. I think this is the simple definition. Okay, students, for mutual induction. Okay, again I'm telling, mutual induction is the phenomenon of production of induced EMF in one coil due to the changes of current in the neighboring coil. Okay, right. See this, take a rod and we are taking that two coils. This is one coil and another coil. Yes, both are placed near to each other, and one coil is connected to the which one, battery, the help of key, and another coil is connected to galvanometer or voltmeter, right? If you have changed the current, flow of current in one coil, yes, the magnetic flux also here what changed in the neighboring coil. In the neighboring coil only induced EMF is produced. Yes, so with the help of deflection, yes, we confirm there is a induced current in the neighboring coil. Okay, students, this is that mutual induction. See this is the one coil and this is the another coil. So we are taking this primary coil and this is that taking a secondary coil. Is there any changes in primary coil? There is also similar changes in secondary coil. Okay, students, if you are increase the current in primary coil, the galvanometer shows high deflection. When you are decrease the current in primary coil, the galvanometer shows minimum deflection. Okay, so based on current changes in primary coil, yes, the induced EMF in the secondary coil, and the secondary coil produced current. Yes, due to the current only the galvanometer shows the deflections. Okay, students, right. Coefficient of mutual induction. Coefficient of mutual induction. At any instant, magnetic flux linked with the secondary coil. At any instant, magnetic flux linked with the secondary coil is directly proportional to the current in the primary coil. Current in the primary coil. Okay, students, therefore I am taking pi is directly proportional to I. Flux is directly proportional to the current in the primary coil. Therefore pi is equal to m into I. If you remove the directly proportional, we have to use equal, therefore equal to m. Here m is the proportionality constant that is called as mutual inductance or coefficient of mutual induction of two coils. Therefore pi is equal to m into I. Okay, now if any change in the current, yes, I set up and induced EMF in the secondary coil, which is given by induced EMF, no, therefore EMF is equal to rate of change of flux, therefore minus d pi divided by dt is equal to minus d pi divided by dt, right? Therefore here if I am substituting instead of pi, what will come? Mi. Therefore minus, so minus d by dt into mi. If m go to this side is m minus di by dt. Okay, m minus di by dt. This is the induced EMF formula. Okay, students, so this one is very important. The magnetic flux linked with the secondary coil is directly proportional to the current in the primary coil. This is very important. Therefore n pi is equal to mi. Okay, students. Okay, this is the coefficient of mutual induction. Okay, students. right? See this, two coils I'm taking. The total length of the coil is L. See, this is black coil. This is the first coil. It has number of turns N1, right? And the blue coil S has number of turns N2. It has cross-sectional area A. Yes, the one coil is connected to the battery, and yes, if I am applying the current, the magnetic flux linked with the secondary coil, that is N2. If any changes in current in one coil, there are induced EMF in the second coil. Yes, this is the mutual induction. Okay, students, you understand? Okay, now factors on which mutual inductance depends. Some factors on which mutual inductance depends. The number of turns. First one is number of turns. Larger the number of turns and larger the mutual induction. Okay, if the coil having large number of turns, it will produce the large mutual induction, and larger the common is cross-sectional area of two solenoids, larger will be their mutual induction. So if a high area also will produce the large mutual induction. And third one is, larger the distance between two solenoids, smaller will be the magnetic flux linked with the secondary coil due to the current in the primary coil. Therefore, smaller will be the value of M. If the distance will be smaller, yes, the distance will be between the two coils is small, the mutual induction is also small. Okay, students, that is the conclusion in this point. Okay, again I'm telling, first point, if the coil having high number of turns or higher number of turns, the mutual induction also higher. And if that area of fractional is of the solenoid, two solenoid is high, it will produce a high mutual induction. And the distance between the two solenoid is if small, it will produce a small amount of mutual induction. Okay, students, right? Okay, and next, yes, see, so this is the book content. Mutual induction: when an electric current passing through a coil changes with time, an EMF is induced in the neighboring coil. This phenomenon is known as mutual induction, and the EMF is called a mutually induced EMF. Yes, this is the definition of mutual induction in our book. Okay, students, so please note it down. Right? See this, I'm taking, this is coil 1 and this is coil 2, right? And this coil is connected to the battery and the current flows, right, like this to this. So if the current flows to the coil around that, what will produce magnetic field. Okay, so this magnetic will present in the second coil also. If the changes in current, the magnetic flux is also changes in neighboring coil. This neighboring coil produced induced EMF. That induced EMF is E2, right? And the flux in the second coil is pi 2 1. This coil has N2 turns. Okay, students, that's why when the electric current passed to the coil, one coil with respect to time, induced EMF in the secondary coil. Okay, students, right? And continuation, yes, I'm explaining that book content. Okay, yes, in last slide I'll explain what is mutual induction. Okay, so due to that reason, just I'm reading. Okay, just you have to follow. See this, consider two coils which are placed close to each other If an electric current I1 is sent through the coil 1, the magnetic field produced by it also linked with the coil 2. Yes, in the figure. Okay. Therefore, let pi 2 1 be the magnetic flux linked with each turn of the coil 2 of N2 turns due to the coil 1, right? Therefore, the total flux linked with the coil 2 is proportional to the current. So please remember, I said no, the magnetic flux is directly proportional to the applied current. From that yes concept, I am taking flux in which coil? Secondary coil? No, that's why the turns is N2 and the flux is 2 1, and the current changes in which coil? First coil? No, therefore the current in first coil I am taking I1. If you remove this proportional constant, sorry, relative proportional, I have to use some constant. That constant is M, proportionality constant of mutual induction. Therefore, N2 pi 21, which is equal to M21 into I1. Therefore, if I am taking M21 this side, the I1 going to downwards. Therefore, N2 pi 21 divided by I1. Yes, there's the mutual induction in the second coil. Okay, students, right? See this, the constant of proportionality M21 is the mutual induction of the coil 2 with respect to coil 1. It is also called coefficient of mutual induction, right? Suppose if the I1 current is 1 ampere, what will come? M21 which is equal to N2 into pi 21 divided by 1, the same value will come, right? M21 is mutual induction of the second coil due to the first one is equal to N2 pi 21, right? And another important point, the mutual induction M21 is defined as the flux linkage of the coil 2 when the current 1 ampere flows through the coil 1. Okay students, please note it down. Again, I'm telling the mutual inductance M21 is defined as the flux linkage of the coil 2 when 1 ampere current flows through the coil 1. Okay students, right? Okay, and see this, when the current I1 changes with the time, an EMF is E2 is induced in the second coil. Says or no? Again I'm telling, when the current I1 changes with time, an EMF is E2 is induced in the coil 2 from Faraday's electromagnetic induction. This mutually induced EMF. Okay, so therefore on mutually induced EMF formula, please remember E is equal to minus M into di by dt. No, so with the help of that formula, E2 is equal to minus d N2 pi 21 divided by t. So N2 pi 21 is nothing but what? That is equal to M21 into I know. Therefore minus d M21 into I1 divided by dt. Therefore M21 is into this side, V2 is equal to minus M21 into di1 divided by dt. Therefore the mutual induction is M21 which is equal to minus E2 divided by di1 divided by dt. This negative sign indicates that mutually induced EMF is always oppose the changes in current, oppose the changes in current according to Lenz's law. Okay, suppose if I am taking that this I1 di1 divided by dt is equal to 1 ampere per second, what will come? M21 is equal to minus E2 divided by 1. Therefore M21 is equal to minus E2. Which one? minus E2. Okay, students, right? Okay, so mutual induction of the second coil M21, which is equal to minus E2, minus E2. Okay, students, right? Okay, right. So mutual induction formula is M21 is equal to minus E2. Okay, students, right. Continuation. Mutual inductance M21 is also defined as the opposing EMF induced in the coil 2 when the rate of change of current through the coil 1 is 1 ampere per second. Okay, so we are calculating the induced EMF, right? So what will come here? M212, which is equal to N1 pi 12 divided by I2. Yes, the same way if you are comparing the induced EMF M12, which is equal to minus E1 divided by di2 divided by dt. Okay, so therefore I am comparing these two equations. So this one which is equal to this one. Okay, right? Okay, students, that is, see this previous one, M21 which is equal to minus E2 divided by di1 divided by dt. Yes, the same way if we go to that 1 to minus E1 divided by di2 divided by dt. Yes, therefore M12 is the mutual inductance of coil 1 with respect to second coil. Yes, it can be shown that for a given pair of coil, the mutual induction is same. Therefore, the mutual induction of one coil is also equal to the which one? Second coil. Therefore, I conclude M21 which is equal to M12. M21 which is equal to M12. Yes, that is equal to M. M is nothing but mutual induction. M is nothing but what? Mutual induction. Okay, students, right? See this again. First one, the flux is directly proportional to current. Flux in second coil due to the current in first coil. From this, with the help of this one, I am taking that mutual induction of the second coil due to the first one, right? Okay, and yes, based on the induced EMF, the mutual induction is of the second coil M21 is equal to minus E2 divided by di1 divided by dt. Okay, students. Okay, and after that, the same way we are calculating the M12 mutual induction, and based on the induced EMF, M12 is equal to minus E1 divided by di2 divided by dt. Okay, so both equations I am comparing, both are is equal, then only mutual induction of the second coil due to the first one is M21, which is equal to mutual induction of the first coil due to the second coil is M12, that is equal to mutual induction. Yes, that means the mutual inductions of the S pair coil is same. Okay, students, right? Do you understand? Okay. See this, the unit of mutual inductance, unit of mutual inductance, right? The unit of mutual inductance is also is represented by Henry. Okay, if I1 is equal to 1 ampere and the N2 pi 2 is equal to 1 bar turns, then the mutual induction of second coil due to the first one is equal to 1 Henry, right? Therefore, the mutual inductance between two coils is said to be 1 Henry if the current of 1 ampere in the coil 1 produces unit flux linkage in the coil 2. Is that 1 Henry definition, right? Therefore, if I am taking that di1 divided by dt is equal to 1 ampere per second, then the EMF in second coil E2 is equal to minus 1 voltage, then the mutual induction of the second coil due to the first one is 1 Henry. Therefore, the mutual induction between two coils is 1 Henry if the current changes at the rate of 1 ampere per second in one coil induced in the opposing EMF of 1 voltage in the second coil. So if the 1 ampere per second current flow in the one coil, it will produce or opposing the EMF in the second coil. Yes, the EMF if 1 voltage pass to the second coil. Okay students, because the mutual induction takes place between the two coils, not in a single coil. Okay students, right? Okay, you have any doubt? No. Okay, right. Students, today class is over, right? Listen on next video. Okay students, right? So tomorrow we'll going to discuss about mutual induction between two coils. Okay students, please go through the mutual induction topic. What is mutual induction and what is the formula? Okay, then only we'll understand the next topic. Okay students.